Worst of both worlds or best of both worlds? If the goal of a plug-in hybrid is to work well, both as an EV and when using gasoline, petrol or gas in everyday English, then the answer depends entirely on whether the PHEV is based on an EV platform or on a traditional internal combustion engine vehicle platform. For a time, a PHEV, being the best of both worlds, was seen as a betrayal and an impure goal. But today, in 2026, it's what manufacturers and customers want, which is why the PHEVs based on EVs are now in ascendancy and increasingly seen as central to strategies for manufacturers to survive the auto industry's great pivot. Meanwhile, combustion engine-based PHEVs, sometimes dismissed as compliance PHEVs, are increasingly becoming lower volume vehicles for the niche of electrified gasoline-based performance vehicles. So, when people say, are PHEVs rising, falling, green, fake, efficient, inefficient, the best of both worlds or the worst of both worlds, the first question should be, which type? But how to answer that when there's no agreed names for the actual two main types? Most often used labels are EREV, originally embraced by regulators and EV fans as a label which excluded any PHEVs that could be described as the best of both worlds, and the broader PHEV, which technically includes all types. Today, as will be seen, the original intent of EREV is lost, and those labels never helped identify what have now become the two main types anyway. In fact, they just cause confusion that feeds mistaken groupthink beliefs as people mentally try to justify terms that have lost their original intent. The result is several widespread misunderstandings about PHEVs. Welcome to One Finite Planet EV tech video on PHEVs that explains the types and debunks some of the widespread and misleading groupthink. Chapters: PHEV history, two types made so confusing by a holy war. Why PHEV types matter, debunking the myths and groupthink, the bypass and why it's an asset and not a betrayal, resolving the best of both worlds or worst of both worlds question, and the conclusion that to understand the future of cars and brands, understanding PHEV types is essential. The PHEV concept dates back to the 1970s fuel crisis work by Victor Wu and later work at UC Davis by Andrew Frank, with early concepts and then prototype plug-in hybrids that were PHEVs built by starting with a conventional gasoline vehicle and then electrifying it, with the goal of reducing the use of fuel without reducing performance. But the first production PHEVs, they weren't on that path, or even designed to solve the same problem. In fact, not even a problem for the same vehicle type. Instead of reducing fuel use by combustion vehicles, the problem to solve was which comes first, the EVs or the chargers? The solution was to add an onboard combustion engine powered generator set, or genset, and build generator-equipped EVs, or more precisely, since generator doesn't necessarily include the combustion engine, genset-equipped EVs. This arrives at a PHEV from the opposite direction and with very different goals. Vehicles designed to meet that best of both worlds goal, to be an EV when driven on battery power, but equipped with an onboard combustion engine powered generator set and engineered to also match gasoline vehicle experience when range, cost or infrastructure makes charging for EV mode impractical. The first production PHEV was this type and produced after BYD having first designed in 2004 and presented a pure battery EV ET show car, and then in 2006 the production-ready F3E decided infrastructure was not ready for pure EVs, and a solution to reduce costs, improve range and overcome infrastructure limits was needed. Now, this picture of a Tesla with a genset on the back may look funny, but it conveys the idea behind what BYD has been producing since the 2008 BYD F3 DM. Would putting a genset on the back of a Tesla make it into a hybrid, or would use of the genset give it a hybrid mode? BYD's logic was it's an EV and the genset adds a hybrid mode, dual mode, DM, because there's the mode where it's an actual EV and the mode where it can act like a gasoline hybrid. Their target was also to make the world's first best of both worlds PHEV, as evident by their dual mode label. Built on EV technology, but not yet a true EV platform, and given battery prices at the time, expensive. It was a learning experience and no instant marketing success. The next Genset-Equipped EV was that first 2010 to 2015 Volt model from GM, world's largest car maker from 1931 all the way up to 2007, and producer from 1996 to 2003 of the EV1, world's first mass-produced, purpose-built EV for modern times, which made them another company able to start with EV know-how. Just as GM's history is so questionable, it inspired the film Who Killed the Electric Car, the history with the Volt could arguably inspire Who Killed the Genset-Equipped EV. Note that while both types did die off, neither really died, and most likely there was no conspiracy, just some incompetence. With their Genset-Equipped EV, GM marketing created their problem. GM felt the Volt should not be viewed as a type of hybrid, so they coined their own label, EREV, EREV, for Extended Range Electric Vehicle. In practice, it was more than just an EV that could unlock additional range. It was also efficient when driven on gasoline, an early best of both worlds candidate, although given battery costs at the time, also an expensive one. While also being efficient when driven on gasoline for when charging's a problem may sound like a bonus, passionate EV fans saw it as misleading. But what really made it worse was GM's marketing claimed that the engine never powers the wheels. And since, as did BYD for the F3DM in order to achieve dual mode, GM engineers equipped the Volt with a clutch bypass, a requirement even more necessary then than today to also be economical when driven on gasoline at highway speeds. Meaning, although it's not the default that it is with combustion engine hybrids, there are times when the engine drives the wheels. Range extended, but not just an EV able to travel further per charge, also practical even without charging. Here's the twist. While it could be thought, why would environmentally conscious consumers complain about the presence of a feature to reduce fuel consumption? The mindset was, if the vehicle is promoted as being a type of EV, adding a hidden feature that means owners could just drive their cars on gasoline is cheating. Best of both worlds is not still really a pure range extended EV. While for those fans, best of both worlds meant a betrayal, no longer really purely a type of EV, it was an even bigger problem for regulators. The California Air Resources Board, CARB, wanted subsidies for EVs with a range extender, but not for vehicles that are also practical when owners drive their vehicles on gasoline. By 2012, they had a formal definition of a range extender. They abbreviated it to BEVx, as described on screen. They focused not on the technology to make operation on gasoline practical, but strict specific restrictions that resulted in only one vehicle ever complying, a special California REX version of the BMW i3 that was software limited to use only 1.9 gallons of its 2.4 gallon fuel tank. This meant there was now an official definition of range extender electric vehicles, specifically designed to only allow very limited driving on fossil fuel power. Anything else was now merely considered a plug-in hybrid or PHEV. The name GM coined to describe EV-based best of both worlds hybrids, EREV, and variations like REEV and BEVx, instead came to mean only those EV-based PHEVs with limited ability to be used on gasoline, disqualifying those with a clutch bypass like GM's own Volt, and effectively all others until the technology changed in 2019. By 2014, Tesla had announced a very different solution to the chicken and egg chargers versus EVs problem, their own charger network. BYD targeted EVs for specific industries with their own chargers, like taxis, and had a very improved second generation Chin DM best of both worlds plug-in hybrid vehicle. GM had below target sales for the Volt and Cadillac ELR, and BMW was losing money on the i3. Other mainstream brands, to avoid the cost of introducing EV tech, took another strategy and brought back the original combustion engine based PHEV type, more profitable, as instead of being EV-based, a conversion of current vehicles into a hybrid or PHEV by adding a P2 motor sandwiched between the engine and the gearbox. All major gearbox suppliers soon offered gearboxes with integrated P2 motors and/or P2 motor add-ons for their existing gearboxes, allowing anyone to offer a PHEV and without the need to start with an EV architecture. These vehicles flip the concept from an EV that can emulate a gasoline hybrid to hybrids that can emulate an EV. The result was also the reverse of that EREVs of the time targeted, because for these vehicles, it's the EV driving mode that's considered subpar. This led to 3 PHEV vehicle types, as can be seen from the table on screen. Those trying to be the best of both worlds, those designed to be an EV with a limited function gasoline backup, and P2 sandwich PHEVs trying to improve the power and economy of gasoline or diesel-powered vehicles. P2 hybrids quickly dominated the market, and while in almost every case provided a strong performance boost in hybrid mode, they were also later exposed as being far less strong on achieving fuel efficiency targets. While there are still some great performance hybrids, like the Ferrari SF90 and the PHEV BMW M5, the P2 extinction of this type for the mass market began in 2019 and really took hold in 2022 following EU onboard fuel consumption monitoring data from millions of cars and the explosion of genset-equipped EVs. Then, by late 2019, when Li Auto launched their vehicles with a resurrection of the EREV label, there was no suggestion of meeting California definition of extended range vehicle. And improved electronics near eliminated the restriction on the efficiency of gasoline hybrid mode driving. The holy war of 2014 essentially ended as a pragmatic merger and an end to the gasoline mode must be restricted philosophy. As power electronics improved, the double conversion tax dropped from a massive efficiency penalty for EREVs to a minor engineering variable. Now, whether a car has a physical clutch bypass or is a philosophically pure genset-equipped EV, EREV, no longer indicates a philosophical purity, it's merely a technical detail. But that 2019 pragmatic merger, aligning 2 of the 3 original EV types, leaves just 2 types of PHEV, and no meaningful, widely adopted labels to separate them. The next step, the auto industry revolution, triggered by BYD's 2020 platform merger strategy, is covered in a later chapter. That's the history, and while there are no widely agreed labels and no global body to formally define them anyway, I have labels to identify the types so I can explain them just once to save repeating explanations over and over, here in videos or at other times such as when I'm using AI-based research tools. I use P2 hybrid and P2 sandwich. They're industry insider terms, and while not all combustion engine based hybrids are P2 hybrids, as will be seen, the label captures nearly all gasoline engine based PHEV hybrids, and even Toyota has begun the move to an EV based solution for PHEVs. So the real other type, genset equipped EVs. Sometimes I shorten to GEV or just GEEV. It's still a description rather than an agreed name, but the most widely used industry labels, EV first hybrid and super hybrid, they're quite vague, and I still need to explain them to prevent capturing vehicles where brands or fans stretch the definition. EREV and REEV were already problematic, describing one of the goals of the technology rather than what the vehicle is supposed to be. And the full implications after that GM debacle was a term that's evolved from applying only to vehicles with limited or high fuel consumption gasoline modes and no clutch bypass, which eliminates over 80% of EV-based plug-in hybrids so far. Now, why does it matter? Since it was in China that EV-based plug-in hybrids first took off, the term PHEV came to mean something different in China than it did outside China. Words having a different meaning in different countries? It's common. Entree in Australia and France means almost the opposite of what it means in the USA. The confusion only happens when people travel between countries. And now genset EVs are travelling between countries because they're also on the rise in the West. And this leads to situations like, I just test drove this great new plug-in hybrid. It was silent, great fuel economy. I can drive it mostly as an EV as I can charge at home, with a response of, no, don't touch it. I hear PHEVs are being phased out, they're powerless in EV mode, and in reality, have terrible economy. And this is the key problem. For individual vehicles, the specs reveal a difference. But statistics or information about all PHEVs, that becomes meaningless. You need to check which type. For most people in the West, the reputation of a PHEV was established by P2 hybrids. By nature, expensive and complex combustion engine vehicles that never deliver promised fuel economy. P2 sandwich PHEVs are often seen as the worst of both worlds. Yet in China, genset-equipped PHEVs are positioned as some of the ultimate vehicles, suggesting they really can be the best of both worlds. For automakers, GEEVs, generator-equipped EVs, have already proved to be central to key survival strategies in the Great Pivot. And for buyers, understanding which PHEVs are which may help identify which vehicles and which brands are built around strategies more likely to survive it. So, what is the Great Pivot? What's the problem that's such a threat to car makers? And how have GEEVs been proven as a solution? What everyone agrees is that the Great Pivot is a transition away from an industry built around almost 100% internal combustion engine vehicles. But what they don't agree on is the final mix it transitions to. Many believe the endpoint will be near 100% pure EVs. But as recently as 2024, one of the most sceptical major industry voices was still arguing that pure EVs may only ever reach around 30% of the market. Whatever the endpoint, one thing's clear. For at least the next decade, automakers will have to plan for a mixed market. As shown on the screen, in 2020, EVs were still niche enough that some brands thought they could just wait, delay or ignore. But by 2025, and at 25% global market share, EVs had become too significant to just ignore, while the slowing rate of growth meant they were also not replacing everything as quickly as others had hoped. That combination creates the trap. Automakers can't ignore EVs, but they also can't confidently plan for EVs to rapidly take over every market across the globe. Just moving to a mix creates a problem, and difficulty in precisely predicting the mix, an even bigger problem. Vehicles are built on platforms, intended to last for at least one, and ideally many, full model cycles. And a full model cycle is typically 7 production years following the initial development years. But those platforms normally lock in on a vehicle type. Since building an EV on a combustion engine platform, or the reverse, brings a conversion cost penalty, extra cost, extra weight, packaging compromise, or all three. Plus, the optimal supply chains and production systems for EV and ICE vehicles are different enough that even shared factory facilities are a compromise. Supporting both combustion and pure EV platforms can therefore nearly double platform investment. That's the problem the industry faces. Just needing to split production between platforms already lowers production runs on each platform, and that increases per vehicle costs. And the mix can need to be planned years in advance in an environment of changing politics, consumer attitudes and infrastructure deployment, which makes the problem even more challenging. Genset-equipped EVs provide a way out of the trap. EVs that are built on combustion engine, aka ICE, platforms, they're compromised. But gasoline generator-backed EVs built on EV platforms don't need to be. One single EV platform can serve both pure EVs and GEEVs, turning falling electric motor, inverter and battery costs into a competitive advantage against not just hybrids, but combustion engine vehicles generally. Proven? Yes, by the rise of BYD, with over 20 times growth in EV platform vehicle sales from 2020 to 2024. A rise unprecedented in automotive history, from under 200,000 vehicles per year to over 4 million just 4 years later. Ford's Model T was the original mass production miracle, but even Ford didn't go from under 200,000 cars a year to more than 4 million just 4 years later. BYD did. And the less understood fact is that BYD also transformed itself from a majority traditional gasoline car maker in 2020 to 100% electric drive vehicles by 2022. In 2020, over 80% of BYD vehicles with gasoline or hybrid power were just traditional ICE vehicles. And moving to generator-equipped EVs didn't slow their growth. The generator-equipped EVs grew almost twice as fast as BYD's overall sales. While many may assume BYD's growth was simply that of China's largest automaker, no. In 2020 and all of the 5 previous years, BYD never ranked above 17 in China in sales. The climb was rapid: 12th in 2021, 6th in 2022, 2nd in 2023, and 1st from 2024, supplanting VW, number one for over 10 years in China, and the first time ever a Chinese brand was number one in sales. While rankings change a little depending on how you group the brands, not only has BYD's rise pushed one of the previous top 10 global brands out, but so has at least one other Chinese brand, Geely, the world's second largest producer of genset-equipped EVs. First to take notice were Chinese brands, which quickly switched. All the Chinese brands shown on screen now are also following this strategy. And by 2030, expect at least 5 Chinese brands in the top 10 of automakers globally, meaning at least 5 of the international brands from the 2022 lists will be pushed out of that tier, and all of the brands from 2022 losing market share, as well as dealing with the great industry transition. Of major brands, only Honda and Tesla are now without plans for genset-equipped EVs. Even Toyota is forking from only their own hybrids to adding BYD-style GEEVs, and Ford not only has GEEV product plans, but quotes BYD as the company with the strategy that must be matched. The USA may be isolated from Chinese competition at home, but global volumes are essential. Back in 2020, many thought PHEVs had no future. The solution to avoid split platforms was by moving to EVs as fast as possible. The VW CEO previously declared range extenders are environmentally harmful and outdated, and their head of research claimed the technology had no future. But now in 2026, VW, Mercedes, Volvo, Ford, GM, Stellantis are all examples of companies that have walked back previous aggressive pure EV targets, but this walking back is not simply going back to traditional ICE platforms. All these companies that have had to walk back, either, like VW, already have genset-equipped EVs on sale, or, like all the others, have them in the pipeline. While it's not quite unanimous, there's widespread agreement. The great pivot has become a pivot from traditional internal combustion engine vehicles to predominantly EV platforms, with a mix of pure EVs and gasoline power supporting genset-equipped EVs. Groupthink, inspired by the historical idea there are EREVs, where the restricted gasoline mode ensures they're predominantly in EV mode, and all the rest may as well be gasoline vehicles, isn't even true as a philosophy anymore. Yet, review after review of PHEVs of the GEEV genset-equipped EV type begin with the reviewer describing the combustion engine as if it was a vehicle's main power plant. Reality, as shown on screen, there are 3 main ways to create a platform for building PHEV. Electrify an ICE vehicle platform beyond hybrid level by adding a plug and a larger battery, extend a dedicated ICE hybrid platform, or add an onboard generator to an EV platform. These 3 produce different kinds of plug-in hybrid. For a deeper technical explanation, see the video linked in the description. But for this video, the key distinction is simple. Only the genset GEEV approach to plug-in hybrids allows efficient platform sharing with pure EVs and results in vehicles that can compete on price and features with pure gasoline vehicles, hybrids, all the way through to plug-in hybrids. Because only this type allows for best of both worlds attributes. That first way starts with a conventional combustion engine vehicle and electrifies it, with ways to electrify an ICE platform to produce mild, regular and/or PHEVs by adding increasingly large amounts of battery power and electric motors to vehicles as shown on screen. The most common and simplest path to a PHEV is adding a P2 motor sandwiched between the engine and gearbox, and sometimes also a P1 motor to improve stop-start driving. Although a P3 motor placed after the gearbox can give a better EV mode result, it results in significant cost increases and requires deeper platform changes, making it less an ICE conversion and more a dedicated PHEV platform. And it usually results in a platform even less well suited for also producing EVs. Apart from a second-class EV mode, all these combustion-based vehicles are complex and critically don't allow efficient platform sharing with EVs. The second way, Toyota's power split approach, it's starting with a clean sheet hybrid architecture. No conventional gearbox, but 2 main electric motors and planetary gear set, making them a step closer to an EV-based starting point. To make a PHEV, take a ground-up power split hybrid and just add a plug and a larger battery. But while power split hybrids are very efficient in hybrid mode, approaching the efficiency of GEEVs with a clutch bypass, adding a larger battery and a plug doesn't solve their limitations in pure EV mode. In pure EV mode, MG1 must spin backwards rapidly when driving at speed, or force the combustion engine to turn on just to act as a damper, even if the battery has plenty of charge. So, unsuited for PHEVs, and still no platform sharing with EVs. Toyota's industry dominance gives it the volume to allow it to split production between dedicated ICE and this dedicated hybrids platform. But this strategy means you still require a third platform for effectively producing EVs and plug-in hybrids. And Toyota doesn't still have 3 times the volume of key rivals, which is probably why Toyota is actively refining their GEEV technology. The third way is to start with a clean sheet EV platform, then add an onboard generator set. That's the Generator-Equipped EV or GEEV. Here, electric drive is not an added mode, it's the core of the vehicle. One platform that cost-effectively produces pure EVs plus generator EVs that can compete on cost and efficiency with traditional ICE vehicles and hybrids, or be driven as EVs. The on-screen table shows weight, performance data and price for PHEV and pure EV versions of the BYD Denza Z9 GT, with data from the ICE-based M5 PHEV for comparison. To make room for the genset engine, fuel tank and exhaust system, EV battery size is reduced, which is why the PHEV has lower cost and weight than the EV version. And note that while electrification of a combustion engine vehicle boosts performance, a genset-equipped EV is normally down on performance relative to an equivalent pure EV. Understanding why and the true working of genset-equipped EVs requires avoiding 2 common groupthink mistakes. No, electric motors don't produce power. They only transform electrical power from batteries and generators into mechanical power. Second, the electric power from the combustion engine powered genset is not only used to charge the battery. Its main role is to provide electric power direct to the motors. Yes, although it is sometimes also used to charge the battery. To save time here, if in doubt about either of these, you can pause for the on-screen explanations or to see the video content linked in the description. Most people get that an electric motor requires electricity to run, but can overlook that output is constrained by the amount of power supplied. And while the constraint in an EV is the battery, an EV motor power specifications are what the motor delivers when supplied by the battery, what can be missed is that sometimes that same motor delivers less power when installed in a smaller battery version of the same car. And, as with the Z9 GT, the PHEV version is usually a smaller battery version. In this case, down from 122 kilowatt hours to 63 kilowatt hours. Note, the 330 kilowatt TZ226XYZA rear motors of the Z9 and the 220 kilowatt TZ226XYB motors of the PHEV. That these motors are physically the same, with the same windings, magnets, and using the same SiC or silicon carbide power modules becomes clear not only from their identical weight and dimensions, but also from their 360 Newton meter torque specification. These physically the same motors in the PHEV are limited to deliver less power because the approximately half-size PHEV battery can only deliver around half of the EV battery. But the peak power is 640 kilowatts, which is a lot more than half of the EV's 850 kilowatts. Yes, because while half would be 425 kilowatts, if the battery can just deliver 490 kilowatts, then add another 150 from the genset, you reach 640 kilowatts. And that's the general principle. Why in pure EV mode there's less than 640 kilowatts without the genset, and why during full power acceleration in hybrid mode the genset motor is required, even though all power is still delivered through the electric motors. And this is a key specification difference. In genset-equipped EVs, bypass or not, full power is delivered by the electric motors. So it's the power spec of the electric motors, not plus that of the combustion engine. Yes, there are some vehicles where peak power specification is slightly higher than the motor specification, but this is due to the complexity of peak versus sustained power. While the genset plus smaller battery versus the pure EV's larger battery does allow for increased total range, it also normally results in less total electrical kilowatt power to supply the electric motors. But the next key groupthink myth to debunk is no. Unlike with P2 or other ICE-based hybrids, full power is not about mechanical power from the engine going to the wheels. Genset-equipped EVs, with or without bypass, have the same total power. The mechanical link doesn't make a difference. The only impact is on highway cruising fuel economy. This often repeated mistake can be seen in this example. This wrong explanation was even quoted by an AI system and assumed correct before I asked the AI to consider if in reality it was technically possible, and it quickly did the checking and realised it wasn't. People repeatedly assume if there's a mechanical link, that must make it just like a P2 hybrid. This mistake follows from thinking the genset only charges the battery and assuming that, like P2 hybrids, boosting power needs a mechanical link, even though EREVs without a bypass also use the genset and deliver the same boost in power. 3 clues. First, at under around 80 k's, specifications make it clear the clutch mechanical bypass link doesn't work. If the mechanical link was required, the vehicle would be reduced power up until 80 kilometres an hour, just as EREVs would never reach their full power. Secondly, there's no gearbox in the Z9, so delivering maximum power mechanically would only theoretically be possible at a very narrow range of speeds. Thirdly, using the words from that AI after it realised, forcing a mechanical direct drive clutch to snap shut at a high load maximum acceleration event is completely wrong. Remember, mechanical power can only be sent to the front wheels, as AI confirmed. When you launch the car or slam your foot down for maximum power, that direct drive clutch stays wide open. The mechanical link isn't used. If the car tried to dump 152 kilowatts of mechanical power straight to the front wheels, while the 3 electric motors were already dumping massive torque, it would instantly overwhelm the front tyres, shock the powertrain and cause uncontrollable traction loss. Plus, the clutch isn't designed to be able to connect systems that are not already at matching speeds. The clutch bypass link is not an equivalent to the drivetrain of a P2 hybrid and normally can't be used for full power, while as the specs reveal, the electric motors can. Note, the bypass link is a very, very different and far more restrictive mechanical link that only helps efficiency and no, is not a way of boosting power for genset-equipped EVs. Anytime full power is needed, it has to be delivered by the electric motors alone by the combined electrical power of the battery and the genset. If engine power was delivered like a P2 hybrid, the power would be 152 kilowatt engine power plus 48 kilowatts to reach the 640 kilowatt. But not as the specs confirm, electric motors able to deliver the full 640 kilowatts. That those rear motors have their power reduced from 330 kilowatt in EV mode to 220 in the PHEV is because when all motors combined are delivering that 640 kilowatt, they're using all the electrical power that's available to the motors. There's no extra power to be gained. EREVs have been considered more pure EVs, not because they're better at EVs, but because they're less useful as anything but a pure EV. The clutch bypass doesn't reduce the ability of the vehicle to be an EV. It improves its high-speed cruising efficiency when being driven on gasoline, which makes it less of a pure EV and more of a best of both worlds. While the original argument was moral superiority goes to the vehicle that discourages driving other than in EV mode, but another view is perhaps the moral authority goes to the vehicle using less fuel when it can't be driven in EV mode. The entire purpose of the bypass of a mechanical engine-to-wheels direct drive clutch is for one specific job: high-speed cruising efficiency by, when running on gas power, and acceleration eases after highway speeds are reached, cutting out the steps as shown on screen. Before recent developments, inverters and electric motors used to lose 8 to 12% of their energy at each step, resulting in losses of 20% by the steps that can be bypassed. But as indicated on screen, those losses can now drop to as low as 5 to 7%. Plus, engine efficiency decreases depending on engine speed, and while the bypass gear ratio allows for the engine staying within its most efficient power band of 30 to 50% of full power with no mechanical link at all, the engine can be at the perfect efficiency level. The end result is, while historically the bypass was the only way to match highway efficiency of the best hybrids, such as those from Toyota, the double conversion tax is decreasing, allowing EREVs to close significantly the gap. For many use cases, the best EREVs can now be close enough to best of both worlds. And at some point in the future, if those components keep improving, maybe everything will be an EREV. Okay, best or worst. Despite the reputation as worst of both worlds, P2 hybrids can be described as a masterclass in giving incredible paper performance. If you take a 250 horsepower turbocharged engine and slam a 100 horsepower electric motor right onto the transmission shaft, you suddenly have a 350 horsepower stoplight rocket. Where the story falls apart is when it comes to being a good daily driver, either as a combustion vehicle or an electrical vehicle, and actually lowering fleet emissions. While there's a performance boost, there's also the weight boost over a conventional combustion engine vehicle or a hybrid with a smaller battery. And that heavier battery results in worse consumption and drivability than a non-plug-in hybrid when not making use of EV mode. Yes, that'll decrease as batteries get better, but it's still there. Now, can that be offset by the benefit of having an EV mode? Well, except the jerkiness factor, the gutless pure EV mode, and the cold start pollution paradox. All explained on screen. What I haven't covered yet is isn't a PHEV carrying extra dead weight of a combustion engine when in EV mode? Almost always the answer is not really. It's one of those things that sounds right, but usually isn't. Check the actual vehicle weight, and normally an exactly equivalent EV is heavier. Even typical for ICE-based PHEVs, the ICE genset battery weighs less than the larger EV battery, resulting in lower total weight. EVs are normally driving around carrying the dead weight of a larger battery than that needed for day-to-day driving, and that larger battery is usually heavier. And of course, even traditional combustion engine cars have a larger and much heavier engine than you need day-to-day. So, how does a genset-equipped EV perform under each of the scenarios? Well, first, while P2 PHEVs can be stopped like rockets, as the car wow Ferrari Purosangue BMW X5M Zeekr 8X drag race video with the thumbnail here and link below shows, they can't match an equivalent, lower priced genset equipped EV. Okay, but what about daily drivable either as combustion engine or electric vehicle and lowering fleet emissions? Well, there's really no combustion mode, just times when the genset is generating electricity to feed the electric motors of battery. Despite saving the weight and cost of gearbox, larger combustion engine and much of the cooling system and alternator, compressor belts, etc., until batteries get substantially lighter, these vehicles are still heavier. And you won't get that lightweight sports car feel. But smooth electric power does a lot to compensate. Most people still find the driving experience significantly improved over traditional vehicles. And for economy, the genset-equipped EVs can even exceed the best hybrids, even when they're in depleted battery mode. And of course, EV mode takes things to another level with silent, lower cost motoring. There's no jerkiness factor. EV mode isn't full power, but unlike a P2 hybrid, it's close. The cold start paradox, it's gone. Full details in an in-depth video on GEEV driving modes to be linked below, but the result depends on what a person considers best of both worlds. GEEVs offer close to pure EV performance while weighing less and more performance than other vehicle types, although with current battery tech, they often do weigh more. For keeping NVH, or noise, vibration and harshness, low, GEEVs achieve best of both by being able to match EVs. But although low NVH is considered the normal goal, sometimes noise, the sound of a burbling V8, scream of a race V12, or the vibration and mechanical feel of gear shifts are actually wanted. They can be emulated, but it isn't the same. The sensory involvement is one of the reasons there's still a role for P2 and other hybrids. It's just a very specialist role. Overall, that sometimes desired worse NVH aside, for most uses, GEEVs do clearly deliver or exceed the best of both combustion-based hybrids and traditional gasoline diesel vehicles, while providing all the benefits of a real EV mode. But do they deliver the best of pure EVs? Splitting the battery source into a genset and a smaller battery can save weight and cost and deliver the best range of any vehicle type, but it also comes with downsides. Performance, although it can beat any other hybrids or traditional gasoline cars, is normally still not quite that of an equivalent pure EV. Although the Z9 PHEV can match the M5 in a 0-100 sprint, the pure EV version can win comfortably. Also, it costs more to service a genset than a battery, but by far a bigger issue is the reduced EV mode range. Do note that pure EV range should be reduced by around 20% when making comparisons, because pure EV range is for driving until zero charge, which is highly problematic in reality, while GEEV EV range is down to 20% or 25% when the genset activates, which is realistic and normally done all the time. But right now, that 20% adjustment, in most cases, is academic. Yes, the Z9 GT and the Zeekr 8X from the drag race video both feature an EV mode fully sufficient for road trips and comparable with many pure EVs, but they're performance vehicles that need large batteries in order to provide enough power for their electric motors. In 2026, most lower priced GEEVs, and particularly most outside of China, where it's changing rapidly, have an EV mode range providing only around 100 kilometres of urban driving. Road trips are going to require stopping at gas stations. Even if they're long range, can mean one stop before, during or after is all you're going to need. While battery improvements will mean far more GEEVs can manage road trips in pure EV mode in the future, in the end, why have a genset if it would never be used? Which brings up the last category, being green. And while P2 hybrids have created a negative impression, in reality, GEEVs can be far greener than most people would expect. Most current GEEV vehicles come from China or are based on tech from China, where PHEVs must meet efficiency standards for both charge-sustaining consumption and EV mode consumption to be branded an NEV. Plus, fleet data is captured and manufacturers penalised if vehicles don't meet a target of being able to be driven as an EV 90% of the time, which is why P2 hybrids end up making only 2% of all new vehicle sales in China, and genset EVs around 12 times more at nearly 25%. More significantly, note the new EU emission targets, as shown on screen. While many saw the move to allow hybrids as weakening of emission goals, the fine print makes it clear they're basically only now permitting GEEV-style hybrids, which weren't even on the radar at the time of the previous standard, and have a target of a 90% reduction in emissions for these vehicles as a result. These regulations and their adoption of e-fuels, two subjects to be explored in full in content to be linked below, but the bottom line is genset-equipped EVs are now central to any realistic plan to dramatically reduce emissions, and those new EU standards, they're not a step back at all. The short version is, while EVs are ideal, the current infrastructure only supports around 50% of people buying pure EVs right now, and it will take at least a decade to fix that. Meanwhile, if everyone else buys a GEEV, which allows people to increase their EV driving over time, then we can have a complete solution from the time the cars are bought without waiting for new infrastructure to be ready and then start people buying the cars. Which means we can be building up a fleet able to be driven as an EV from now instead of waiting for the infrastructure to be ready and then starting on deploying the fleet. Meaning both things can happen simultaneously instead of one after the other, which could easily add 25 years to achieving the goals. Conclusion. The difference matters. PHEVs matter. In China, EV sales growth since 2023 is 56%, but GEEV PHEVs, 110%, with GEEV-type PHEVs outselling the P2 type almost 12 to 1. And now, it's not just China. In Australia, in the 1 year from May 2025 to May 2026, EV sales grew 148%, aided by the Iran conflict, but PHEVs grew 264%. Exactly which types are beneath that PHEV growth is less clear in Australia because there's no breakdown by type, which is just one example of the lack of awareness of PHEV types. Understanding information on PHEVs and making any decisions really requires understanding the two real types. The label EREV in reality just causes confusion because it never indicated capabilities in EV, but only originally whether the vehicle was sufficiently inefficient when driven on gasoline that it discouraged any use other than EV mode. And today, even EREVs are quite efficient when driven on gasoline, while the original 3 PHEV philosophies included EREV with constraints on use on gasoline. That collapsed to just 2 philosophies by 2020, And since then, only one type delivers what really matters most for all but specialist niche vehicles: overall efficiency and the ability to at least come close to best of both worlds. Understanding this requires understanding the two types, which provides an insight into where the industry is heading and the reality that the PHEV type based on EVs that I describe as Genset-Equipped EVs or GEEVs have become critical to auto companies' ability to survive the great pivot. Ideally, if buying a new car, be either a full EV or a Genset-Equipped EV, but choice is limited, since few, other than Chinese brands, have their Genset-Equipped EVs on the market yet, which can mean the main concern is, are you buying from a company with sound future viability, which matters regardless of what you buy. Hopefully this video was useful, and a lot of research went into it. So please like and share if you find it useful, and subscribe here for more technical content, or to the main channel for more on the future in general.